Project is the fully convolutional networks for semantic segmentation. On the left, you have a guy riding a motorcycle, and what we want our model to do is separate out the guy and the motorcycle and create a new image where it masks the guy in a certain color and masks the motorcycle in another color. And so the way that it is done is explained in the wiki article. And so if you want to learn more in detail on what the model is and how it's done, please visit our wiki article. Here is our model. It is rather large, so I'm not going to go into detail in this presentation, but again, just like I said, if you want to check out the wiki, just go look at it there, and you'll see a pretty detailed explanation on how this works. One of the major issues with training a model in Keras is that it is in floating point. However, if we try to use floating point on the FPGA implementation, it's going to take a really long time to run. So what we're trying to do is take that floating point and put it into fixed point representation. And to do that, we need to figure out what the resolution is needed by the model to accurately represent the numbers in fixed point. So we did a bunch of statistical analysis and found that these are the representation that we need in fixed point. The S stands for signed. 8 stands for 8 bits total. So all of the layers have 8 bits weights and 8 bits output. And then the number after the Q stands for the resolution. So Q7 means 1 over 2 to the 7th. Q-4 means 1 over 2 to the -4 is your resolution. So then we tested it out, and this is our results. As you can see, you can not tell the difference between floating and fixed. It is almost identical. There is slight bit of differences, but it's very hard to tell. And if you couldn't tell by now, the left one is floating and the right one is fixed.
Okay, and this is our software wrapper to interface the camera, the ARM core, and the FPGA. What you're seeing here is the top level module of our Z board. Thread 1 and Thread 2 is being operated by the ARM core. The accelerator is the FPGA. In Thread 1, we're using OpenCV as a wrapper method to communicate with the camera to transform the input frame into an input buffer that is acceptable for hardware accelerator. After our hardware accelerator returns an output, it will do a bilinear upsampling, which will result in our final output frame. The final output frame will be fed to an HDM driver, and then that frame will be displayed onto the monitor. The reason we have the accelerator and the bilinear upsampling model separate is because we don't want to start thread 2. If we put the bilinear upsampling in the accelerator, thread 1 will be running most of the time while thread 2 will be idle, which is the reason we have 2 threads, and the computation is divided between the accelerator and the bilinear upsampling.
This is the overview of hardware accelerator. Basically, for all the convolution layers and file layers, they happen sequentially, but for each layer, this is the design. Basically, all data are coming from DRAM, and the result is coming back to DRAM. And in between, first we store all the weights into the BRAM, and then we stream all the input cache, squeeze core, expand core, and output cache, so that it can happen in parallel. And in this way, we can fully utilize the resources in the FPGA. This is the utilization result. Basically, we can see since the utilization is above 90%, so that is spreading all over the FPGAs. And the red part is our expand core, the green part is squeeze core, and the yellow part is for HDMI output. So for the accelerator itself, it achieves 15.2 frame per second, which is not bad. But when we embed them with the ARM core, that is other process, and the frame rate drops to the 12 FPS, and we can see the CPU utilization is high, so we can improve more.